welcome you all to this video lecture, and today we discuss steady state error. So there are three basic properties that we need to discuss for control design, and first one was transient response, second was the steady state error, and third was the stability of the system. So we already discussed the steady state response, transient response, stability. Now it's turn of the steady state error. Now let's see what is steady state error and how we defined it and how we can use it for controller design or for analysis. So basically, if we start with the introduction of steady state error in this video, so I told you for design and analysis purposes. So first part is the transient response, then the stability, and then the steady state error. So we already discussed the transient response in chapter where we discussed that time analysis, and then we that is in chapter number 4, and in stability in previous chapter number 6 we discussed Raoult's Harvard's criteria and stability in journal. Now, in this chapter, we will look at what is steady state error and how we can incorporate this for designing purpose. Okay. Now, first of all, let's start. What is steady state error? So, as a definition, if we say that steady state error, so this means that we are talking about after transient response, where things are settled down in the system. So steady state error is the difference between the input and the output for a prescribed test input as t tends to infinity. So the main idea here is that you have to look for the output response after transient response where things are settled down. That's why he put t tends to infinity here. So test input used for a steady state error analysis and design are summarized in table. So now I told you that whenever we have to do some analysis, so we need some standard input so that we know that how a system behave with particular input. That help us actually also to compare with other system as well. Okay, now what are these inputs that we normally use for steady state analysis? So this is noted in table 7.1. So in order to explain how these tests are used, let us assume an example. An example is a position control system. Okay, so where the output position follow the input recommended position. So assume that you have a satellite and you want to make a particular position in an orbit. Okay, so system input represents constant position, thus they are useful in determining the ability of the control system to position itself with respect to a stationary target, such as satellite in geostationary orbits. Okay, so example we take is very simple one and a satellite one where we want it to move it into a particular orbit. So an antenna position control is an example of system that can be tested for accuracy using step input. Okay. Now let me go through this table and we discuss it further. So this table tell us the three possible. So you can move on further, but the idea is the same. So if we look at here on the left side, we have waveforms, then we have a name, then we have physical interpretations of these inputs, then we have time function, then we have the Laplace transform of that time function. So first wave our first test input is the step input, name is step. Okay, we have a it means that we want a particular constant position, so we give a step input. So if we look at the function in time domain is 1, if we look at the Laplace is 1 by s. Similarly, the next one is the ramp input. So we call it ramp because it has a linear relation as t tends to infinity, r tends to infinity. So it is increasing linearly with slope of 1. So this is also known as ramp. So we call it for constant velocity. So step is constant position, ramp is constant velocity, and the time function is t, and Laplace is 1 over s square. Similarly, the third one is a parabolic one, and we call it constant acceleration, and the time response 1 over t, 1 over 2 t square. So this is equal to 1 over s cube. So these are the normally inputs that we can use. We can define higher order as well. Okay. So now this is an example shown in a figure where we have a satellite and uh, we want to move it into a different orbitic position. So we can say that test input for steady state error analysis and design vary with target type. Okay, so either we have a orbit by a satellite or we have a missile to track something, so it can vary. Okay, so ramp input represents actually constant velocity to a position controlled by their linear decreasing amplitude. These waves can be used to test a system ability to follow linear increase input and eventually to track a constant velocity target. So for if we have to look for velocity, then we can use the ramp input. Similarly, for acceleration we have to use the parabolic input that we discussed in table 7.1. Now one thing, and which is the most important thing, is that whenever we have to discuss the steady state error analysis, so this is the whole discussion is useful, or formula that we develop is used when we have a stable system. So this is very important. Otherwise, for unstable system represent loss of control in steady state and are not acceptable for use at all. So be careful that the technique for calculating the steady state error only apply to a stable system. If your system is unstable, you are unable to apply this formula. This will give you the wrong information. Because steady state error only occurs when we have some steady state value. If we have unstable system, there is no steady state value. Okay, how we evaluate the evaluation of steady state error? So for that case, let's consider a figure here. That is the figure 7.2. So this figure has two graphs. The first one is graph A and second is graph B. So if I look at graph A, look here, the input is the step input, a constant input. Okay, and we have two outputs. Look here, this is the first output that is represented by output 1, and the second is represented by output 2. In horizontal axis we have a time in seconds, and y-axis we have the output. Now output 1 is reaching the input. Okay, but output 2 is unable to reach the input. So this means that output 1 at steady state is reach the input as t tends to infinity. So this means that output 1 has zero steady state error. But look here, in output 2 there is a constant difference between input and output, and this constant difference is known as the steady state error. So similarly, if we look at the velocity input, that is the ramp, So this is the input system, okay, represented here by this arrow. This is the input, this is the ramp input, this is again the amplitude of the y-axis, and x-axis represents the time in second. Now if you look at the output, the first output is reaching the ramp, so this means that steady state error is 0, but second output has some constant values after some time, and we call it as the steady state error. But if you look at the third output, which is interesting here, it has different slope as compared to these two outputs. So this means that due to different slopes, as t tends to infinity, the difference between these two curves keep on increasing. So that the error is also increasing. So as error increasing, error goes to infinity as t tends to infinity. So this means that for output 3 we have infinite error. Okay. Now, how we look at this, let's consider a block diagram to understand the concept, how we will calculate them mathematically for this error calculation. So, let us now look at the error from the perspective of more general block diagram. So, look here. This is the unit feedback block diagram. So, this is figure 7.3. We have to look at first um, B figure, then we will move to A. I told you how he made A. So this is a very similar figure that we know and we will work normally. So where we have input, we have output, we have feedback, we have error, and we have transfer function, and we have unit feedback here. Okay. Now this is negative feedback. So look here. For this chapter, we discuss the steady state error mathematics, especially when we have unit feedback. Okay, so if we have other than unit feedback, so formula might be a bit changed. Okay, so that's why most of the cases we have to discuss for unit feedback. So the formula we develop is only work for unit feedback. Okay. So if you have if you have some sensor dynamics in the feedback, so in that case you have to include that and calculate it. You are not allowed to use the uh, formula that is developed for unit feedback. So look here, this is the, if what we are interested in this output, that is the error, how we make it to represent an error. So it's very easy. If I extend this thing further, it will move. I have to move this block in the feedback. So make this an error. So output. So I make this an output. Okay. Now this becomes output, and so in that case, the transfer function of error to input becomes 1 divided by 1 plus G. Okay, so that's why he is redraw the figure here, okay, to calculate for that. Now, if we consider this general form, and we have to consider two blocks here to analyze the steady state error. Okay, so system in 7.4, this is 7.4 figure, where we have two block diagrams. So this is the first one and this is the second one. So first one is the finite steady state error for step input, and second is zero steady state error for step input. Okay. So if I give step input here, we have a finite error. If I give step input here, we have zero error. So what happened? If I wrote the output here, so output is equal to, if I want to write the equation of output, so in time domain, I can say that actually error is the difference between R minus C, okay, from the block diagram, R minus C. So I wrote here. Now, if I say that in time domain, this R of S is represented by R of T, E of T for error, and C of T for output. So, if I want to write the equation of C of T at steady state, okay. So for steady state, this is equal to K times error, okay. So I just plug in the equation that steady state output is equal to K times steady state error. So if I want to calculate the steady state error, this becomes 1 over K times steady state output. Okay. Now if you look at, this is the equation for error that is represented in 7.1. So if I want this to be 0, how I can do it? As I increase the value of K, the steady state error will start decreasing. But we are unable to make it 0. How we make it 0 if K tends to infinity? So what this means? This means that we have constantly apply some input so that make this equal to 0. Or in other words, when this is the case, that we need some integrator, okay. When we plug in the integrator, that will make this system goes to 0, okay. So that's why in second case we have 0 steady state error, okay. Let's the larger value of K for 7.1, the smaller value of it, but it never goes to 0 unless otherwise K is infinity. So the for pure gain, we are unable to make this steady state error 0. So if the forward path is represented by integral as we did in second figure, what happened? So the resultant error, steady state error, is 0 for step input. How it is possible? For example, we have output is C of T increasing, error will decreases. Okay, since error is equal to R minus T, this decrease will continue until there is a 0 error. Okay, but there will still be a value of Ct, since an integral can have a constant output without any input. Okay, so because you know that if there is no input, when we integrate 0, it becomes a constant. So this means that we need to introduce a motor here that gives a constant input, okay, when there is no input to the system. So for that reason, it does not return to its initial position. We have an for example, a motor can be represented as simply an integral that can provide an extra input to the system. A voltage applied to the motor will cause the rotation. When the applied voltage is removed, the motor will stop and remain at its present output position. Now, since it does not return to its initial position, we have an angular displacement output without an input to the motor. Therefore, a system similar to figure 2, which uses a motor in the forward, can have a 0 steady state error. So, the basic idea is very simple. We need a constant input. So that's why we introduce a integral here that makes this output goes to 0, steady state error goes to 0. So here we eventually go for two types of systems where we can have a constant steady state error and we have a error that goes to 0 with same controller with K and K by S. So from here, the basic idea we learn that if we have a constant steady state error, then we need to introduce an integral to the system that makes the error to 0. So the thing that we learn from design point of view, that if we introduce an integral to a constant steady state error system, it will make it 0. Or in other words, uh, when we introduce an integral to the system, this means that we are introducing an infinite gain to the system from equation 7.1 that makes steady state error 0. So this is the basic idea, and I will stop here and we will continue further. And this is just an introduction about steady state error. So if we go through what we learn, what is steady state error? Steady state error is the one, it is the difference between the input and the output when t tends to infinity. In other words, steady state error will calculate it after transient response, and this is only applicable when you have a stable system. So 7.1 tell us that if you have a constant steady state error, so you only make this steady state error 0 when you introduce an integral to the system. That gives an infinite gain to the system. Okay, we know that when 1 over infinity is actually equal to 0, so that's why integral, when we introduce integral to the system, it provides an infinite gain to the system and make the constant steady state error equal to 0. So be careful, integral will only work for a constant steady state error. Okay, I will stop here. We will continue further in coming video. Thank you.